Welcome to the digital carrier modulation. So this is the CO3 of the digital communication. So we are going to study about the digital carrier modulation in the CO3. So as we already studied in the CO2, the baseband digital transmitter and receiver, where we know the source of the information. There are three types of the digital information and the textual information and analog information, whereas the digital information directly can be fed to the pulse modulate, whereas the textual information feeding to the encode and then the pulse modulation, whereas for the case of the analog signal, we are converting it to the sampling and quantization and encoding, that is the analog to digital conversion format, and then directly digital. So that the pulse modulation having the input is the digital format, either is the directly from the digital data or a textual information or analog source. So then this pulse modulation and then transmission and through the channel, and again at the receiver side the receiving and demodulate, and again after demodulation we are going to get a three kind of the information, such as a directly digital information or a textual information or analog information. Okay, this is what we have studied in the baseband digital transmission. So the name baseband digital transformation is nothing but here there is no modulation technique here. So directly after the getting the digital data, we are doing the pulse modulation and then we are transmitting. So there is no carrier modulation or it is a modulation techniques. Whereas now we are going to study about the passband digital transmission. Passband digital transmission, in the sense we are doing the modulation by using an analog carrier signal. So here the transmitter we are using as a carrier signal, but the modulating signal is again analog digital information only. This digital information either again we are getting either from the digital gadgets or instruments such as a computer directly, or a textual information or analog signal converting by digital format by using the analog to digital conversion. So we hear the pulse modulation, it is analog, it is a digital signal, but we are modulating with the carrier signal as we have done in the analog communications. So here the carrier is the analog, but digital information, this source of information is the digital form. Again the channel is the transmitting channel, and again the receiver side similar to the analog communication, again we are in the local oscillator and the demodulation. So this is what the analog format, and then we are getting the demodulation. After the demodulation again we are going to the converting back to the either digital information or textual information or analog information. So this is what the passband digital transformation. So the difference between the passband digital transformation or the baseband digital transformation, in the passband digital transformation we are doing the analog carrier signal, so that we are doing the modulation, up converter and down converter. So this is what the passband digital transformation briefly outlined. Say for example, we are getting a digital data, we are modulating with the carrier signal. Okay, so the digital data may be getting, say for example, from a computer or any other gadgets or any from the analog source while converting the digital format. So after the modulation, carrier modulation, we are going to get this type of the signal. This is what we are calling passband digital transmitter signal. This is a transmission link. At the receiver side again we are getting the local oscillator and multiplying with the signal, and then again demodulation we are going to get the digital data. So this is the briefly outline the passband digital transmitter. So now before going to actually the passband digital transmission, so what is the digital signals and certain fundamentals we are going to study in this slide. So usually in addition to being represented by an analog signal, information can also be represented by a digital signal. So for example, a 1 can be encoded as a positive voltage and 0 as a 0 voltage as shown in the below. So this is a digital information 10110001. So this is what we are converting these ones and zeros to a voltage level by using a line coding, as we have studied in the baseband digital transmission. So level 0 it is the 0 volts, and 1 stands for the A, magnitude of A of the analog signal. This is what the waveform of the corresponding to the digital information. So usually we have already studied the bit rate while we are studying the PCM, pulse code modulation. So what is the bit rate? Here the bit rate is defined as the number of bits transmitted over 1 second. So this is what the definition already given. Okay. Suppose now I will ask you one question, quiz question here. What is the bit rate for the digital signal shown in the figure? So now a signal has been shown here, a digital format. So what is the bit rate? So this answer we have to get it. So the answer here it is, since 1 second, for you observe in the figure, it is a 1 second, how many bits are there? 1, 2, 3, 4, 5, 6, 7 and 8. So that 8 bits are available for the 1 second, so that is the 8 bits per second. This is what the answer for the bit rate. Again another quiz question. What is the bit rate? Already we have studied. Now what is the bit period or duration? So this is another quiz question. So bit period is nothing but a reciprocal of the bit rate, so that 1 by 8 bits per second, or you can say 0.125 seconds. Now we are continuing the digital signal. So until now whatever the digital signals we have studied as a binary format. So this is what we are calling M array format. We already studied in the M array format in the CO2. So a signal can have more than 2 bit levels are shown below. In this case we can send more than 1 bit for each level. So you can say the each bit level, say for example here it is a M array, M is equal to 4. So 1 bit period, 2 symbols we are transmitting here. Okay. So in this case what is the bit rate for this digital signal? So each pulse is represented by 2 bits. So each pulse is represented by 2 bits. See, say for example here is 1 1 1 0 0 1 1 0 1 0 0 0 0 0 0 1 0. So each bit period, each pulse, okay, we are representing by 2 bits. So that hence in this case the bit rate is 8 into 2, 16 bits per second. So this is what we are taking the M array. M is equal to 4 level. Now signal elements versus data elements. So most of the time we are doing the signal elements and the data elements. What is the difference between these two? So here you are represented by a left side and a right side. A left side you can see, observe here, for each pulse we are represented by 1 data element. So that we are calling the 1 data, that is nothing but a binary bits we are calling a data elements. Here for 1 pulse we are represented by 2 bits. So that each pulse having the 2 data elements. This is what a representation of the data elements. So a data element is the smallest entity that represents a piece of information, that is a bit. A signal element, now on the other hand the signal elements is the shortest unit time wise of a digital signal. In other words, the data elements are what we need to send, signal elements are what we can send. So data element generally it is represented by bits, whereas the signal elements we are represented by a units. So what is that one we are going to study here is briefly outlined like this. Say this is a rectangular pulse we have shown here, it is a TB bit duration. So this is what we are calling a digital signal, is a 1 and this is a 0. This is what we are calling data elements, whereas the signal directly actual signals are represented by this one. So 1 bit period, how many sinusoidal signals we have sent it. So for 1 bit on, this is a signal, and off there is no signal transmitted. So this is the what we are calling a signal element. So for binary data is on, signal has been sent, off, signal is not sent. So this is the data element, this is the signal element. Similarly, if you take M array, this is what we call M array 4 levels. We are representing 1 1 1 0 0 1 and 0 0. We are calling as a data elements, whereas correspondingly these are the sinusoidal signals with the different amplitudes represented by corresponding to the different data elements. So this is representing as a signal element. So here the data elements we want to indent to send, whereas the actual signals we have sent here this one. So this is what we are calling a data elements. where actual signals we are sending we are calling a signal element. For example, in the digital carrier modulation, we are representing a modulated signal in terms of a binary data, that is the zeros and ones like this. So a 0 is generally represented by a data element. So 0, 0, these are the data elements. Similarly 1, 1 are also data elements like this. So when the carrier signal we are multiplying here, so when there is no signal, okay, and when the signal is high, this is the signal we are passing. There is no signal and the signal is passing. So when is a 1 signal is passing, 0 no signal passing. Similarly BFSK and BPSK we are going to study. So you have to understand here, this is the data elements, correspondingly what are the signals that have been transmitted, we are calling as signal elements. Now another important thing in the digital carrier modulation or a digital modulation, bit rate, baud rate and also bandwidth. Now presently we will study the bit rate and baud rate. So bit rate is the number of bits transmitted over a second. It is already defined earlier. Baud rate on the other hand is the number of signal units transmitted over a second. So we are already studied again the signal elements and data elements. This is the difference here. So bit rate is the actually digital bits we are transmitting over a second, whereas the baud rate is the number of signal units. As we have observed previously, the signal units are nothing but a number of carrier signals for over a one period or one pulse signal transmitted. So this is what we are calling baud rate. So usually the baud rate is less than or equal to the bit rate, depends on the number of levels transmitted. So baud rate is equal to bit rate by number of bits per signal unit. So generally the mathematically represented FB is the bit rate, N is the number of signal elements, then we can take a baud rate is nothing but FB by N. So let us take a example here. So the top figure you can showing here a digital signal with the two levels. The two levels in the sense nothing but a binary data. It is a bits only, binary data. So that is the 1 is the high, 0 is the low. So like this we are representing. So for this second is already seen the earlier we have seen the bit rate. Bit rate is nothing but a number of bits transmitted over a 1 second, number of bits. So that how many number of bits per 1 second, here is the 1 second, so that number of bits are 1 0 like this, 1 0 1 1 0 0 0 1. So number of elements is 8. So that bit rate is simply 8 bits per second. And also for each case again the sinusoidal signals are the elements we are transmitting, so that it is the baud rate also the same thing. So FB by N, where the N is nothing but here the 1 only, so that number of bits is 0, either 0 or 1. Whereas the number of levels is 4 levels here, it is the M array, 4 array. So that each pulse signal we are transmitting the 2 bits here. So that bit rate you can say 1 1 and 1 0 0 1 like this, so 8 into 2, so that 16 bits per second. Whereas the baud rate is again the same. Since it is the one pulse, we are saying the one signal element only. So one signal element and one signal element and one signal element like this, 8 signal elements we are saying. So bit rate is the 16 bits per second, whereas the baud rate is 8 bits per second. So it is the baud rate is nothing but a number of signal elements we are transmitting. This is what we have to understand. So now let us see the few examples to understand better way. So example 1, an analog signal carries 4 bits per signal element. So 4 bits per signal element. If 1000 signal elements are sent per second, find the bit rate. So baud rate is equal to 1000, since it is if 1000 signals are sent, so that already again 1000, number of elements is N is equal to 4. So that the bit rate is nothing but 4000 bits per second. Another example, example 2. Let us take example 2 as an analog signal has a bit rate of 8000 bits per second and the baud rate is of 1000 baud. How many data elements are carried out by each signal element? How many signal elements do we need? So you can understand here bit rate is 8000 bits per second, baud rate is 1000. So that automatically you can say that 8000 by 1000 we are going to get baud rate is data elements is 8 bits per baud. Then the number of signal elements, so the L is equal to 2 to the power of 8, 256 levels signal elements are there. And then bandwidth, there is the important thing in the communication system is the bandwidth. So the actual bandwidth necessary to propagate a given bit rate depends on several factors. So digital transmission bandwidth is a crucial point. So that the actual bandwidth necessary to propagate a given bit rate depends on the several factors, including the type of encoding and modulations used, the type of filters used, system noise, and other desired error performance. So these are the three factors define the bandwidth. So the ideal bandwidth generally used to for comparison purpose only. The relationship between the bandwidth and bitrate also applies to the opposite situation. For example, for a given bandwidth B, the highest theoretical bitrate is 2B. Okay, so with this one, a brief, very basics for the digital carrier modulation systems.